The prototype sat on the workbench in a modest facility outside Salt Lake City, Utah, in early 2005. It didn't look revolutionary at first glance, a black rifle with clean lines and a forward-mounted rail system, but every dimension had been calculated for a specific mechanical purpose. Alan Zitter stood beside it, reviewing the technical drawings that mapped 7 interconnected systems onto a single receiver platform. The rifle represented 3 years of concentrated engineering work, driven by a simple observation: existing hardware treated modularity as an afterthought, not as a foundational design principle. Robinson Armament had built its reputation on the M96 series, but Zitter recognized that market expectations were shifting. Users no longer wanted a single optimized configuration. They wanted adaptability, the ability to reconfigure a device for different calibers, different barrel lengths, and different operational profiles without sending it back to a manufacturer or requiring specialized tools. The challenge wasn't creating any one of those features. Several designs offered caliber conversion, others featured quick-change barrels, a few provided ambidextrous controls. What didn't exist was a system where all these capabilities operated as an integrated engineering solution rather than a collection of compromises. The XCR's first tier established the foundation, a monolithic upper receiver that housed the entire operating system. Unlike conventional designs, where upper and lower receivers shared structural loads, the XCR's upper bore all mechanical stress from the operational cycle. This decision cascaded through every subsequent tier. By concentrating structural responsibility in the upper receiver, Zitter created design freedom elsewhere. The lower receiver could focus purely on the trigger mechanism and magazine interface. The stock could fold without compromising system integrity. The barrel could detach and reattach with consistent return to zero because the upper receiver maintained all critical alignments. The second tier introduced the barrel system. A quick change mechanism allowed users to swap barrels without tools, but more significantly, different barrels brought different calibers. The XCR could transition from 5.56 45mm NATO to 6.8mm Remington SPC to 7.622 to 39mm Soviet with nothing more than a barrel change and the appropriate magazine. Each caliber transformation maintained the same core operating group, the same controls, and the same sight picture. This wasn't conversion in the traditional sense, requiring parts kits and fitting procedures. This was true modularity, designed from the beginning as a single system capable of multiple expressions. The rifle's presence in that Salt Lake City workshop represented a philosophical departure from decades of engineering convention. It asked a different question. Not how do we optimize this for a specific role, but rather how do we create a system that can adapt to multiple roles without losing mechanical integrity? The answer lay in those 7 tiers, each one enabling the next, forming a cascade of engineering decisions that prioritize system coherence over feature accumulation. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Alan Zitter understood the constraint before he began designing. The American market in the early 2000s offered 2 paths for modularity, and both had fundamental limitations. The first path: create a platform with optional conversion kits that required specialized tools, technical knowledge, and often factory support. The second path: design a device so general purpose that it performed adequately across multiple scenarios, but excelled at none. Neither approach satisfied the operational reality Zitter observed. Environments where caliber requirements, barrel length needs, and accessory configurations changed faster than logistics could support platform-specific equipment. The pressure wasn't merely commercial. Robinson Armament operated in a market segment where innovation carried substantial risk. Established platforms dominated official procurement. The AR-15 pattern had become the de facto standard for American rifles. The AK pattern served similar functions internationally. Any new design had to justify its existence not through marginal improvements, but through capabilities that existing platforms simply couldn't offer. Modularity as a feature wasn't enough. The XCR needed to demonstrate modularity as a core engineering principle that solved real operational problems. Zita's background informed his approach. He had spent years working with the M96 platform, understanding both its strengths and its limitations. He recognized that true adaptability required more than swappable parts. It required a fundamental rethinking of how these systems integrated their core mechanical components. The XCR's third tier, the gas system, illustrated this principle. Rather than a fixed gas block calibrated for a specific barrel length and pressure, the XCR featured a self-regulating mechanism that automatically adjusted for different configurations. A short barrel generated higher port pressure. A long barrel reduced it. The gas system compensated without user intervention, maintaining consistent operating characteristics across the platform's entire configuration range. This engineering decision created technical challenges. Self-regulating gas systems were known in design, but integrating one into a platform that also supported multiple calibers and quick-change barrels required precise mechanical tolerances. The gas piston had to operate reliably across the pressure ranges of different ammunition types. The barrel interface had to maintain seal integrity through repeated attachment and detachment cycles. The carrier group had to function smoothly, whether the setup was configured as a compact close-quarters arrangement or an extended marksman variant. Financial pressure accompanied technical pressure. Developing a genuinely modular platform required tooling investments without guaranteed market acceptance. Every manufacturing decision carried cost implications. The monolithic upper receiver demanded more sophisticated machining than conventional split receiver designs. The quick-change barrel system required precision that exceeded standard manufacturing tolerances. The self-regulating gas system added parts count and complexity. Each tier multiplied development costs, while the market remained uncertain about whether true modularity represented genuine operational value or merely engineering novelty. Zita proceeded anyway, convinced that the engineering logic was sound. The 7 tiers weren't features added to satisfy a marketing checklist. They were necessary mechanical elements of a single coherent system. Remove one, and the entire modularity promise degraded. The question wasn't whether the market would immediately embrace the XCR. The question was whether operational requirements would eventually demand exactly what the XCR offered. The mechanism's logic emerged from a single engineering insight. Modularity fails when it requires mechanical compromise. Traditional conversion systems asked users to accept reduced reliability or performance when reconfiguring a device. Gas systems calibrated for one barrel length functioned poorly with another. Magazine wells, designed for specific patterns, required adapters that introduced stability or feed angle issues. Folding stocks created either weak attachment points or bulky mechanisms that offset any compact storage advantage. The XCR's 4th, 5th, and 6th tiers addressed these compromises systematically. The 4th tier controlled the operating interface. Every control, lever, and button a user touched during operation. Zita designed these as ambidextrous from the beginning, not as aftermarket additions. The charging handle reciprocated on either side. The magazine release functioned from either hand. The safety selector provided equal access for left or right-handed users. This wasn't accommodation for preference. It was engineering for adaptability, a system that could change calibers and configurations but locked users into single-handed operation had only solved half the modularity equation. The 5th tier tackled magazine compatibility. The XCR's lower receiver accepted multiple magazine patterns without adapters. Standard AR-15 magazines, with their widespread availability and proven reliability, fit directly. This decision reflected practical engineering rather than platform loyalty. By 2005, AR-15 magazines represented a mature technology available globally. Requiring proprietary magazines would have undermined the XCR's core value proposition: operational flexibility in diverse logistics environments. The lower receiver's geometry accommodated this compatibility while maintaining structural integrity and trigger mechanism performance. The sixth tier integrated the folding stock mechanism. Conventional folding stocks connected to the receiver through hinged joints that introduced flex or required substantial reinforcement that added weight. The XCR's monolithic upper receiver design allowed a different approach. With all operating stresses concentrated in the upper, the stock could fold without compromising mechanical strength. The folding mechanism itself was engineered for simplicity. A single latch released the stock to fold alongside the receiver, reducing overall length for transport while maintaining immediate deployment capability. When extended, the stock locked solidly with no perceptible movement, because the upper receiver's structural design eliminated the need for the stock to contribute to system rigidity. These three tiers, operating controls, magazine interface, and stock mechanism, functioned as the human interface layer of the XCR's engineering philosophy. The first three tiers established the mechanical foundation: receiver architecture, barrel system, and gas regulation. These middle tiers translated that mechanical foundation into operational capability. A system might function perfectly as an isolated mechanical unit, but if users couldn't adapt it quickly, or if logistics constrained its flexibility, the engineering became theoretical rather than practical. The seventh tier completed the system. The rail interface provided attachment points for optical sights, illumination devices, and other accessories. The engineering challenge wasn't simply mounting a rail. Hardware had featured accessory mounting for years. The challenge was maintaining zero across configuration changes. When a user swapped barrels or changed calibers, optical sights needed to maintain the point of aim. The XCR's monolithic upper receiver again proved decisive. By keeping all mounting surfaces integral to the receiver that housed the barrel attachment and gas system, the device preserved sight alignment through modifications that would have disrupted it on conventional platforms. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing revealed the gap between theoretical engineering and practical implementation. The first XCR prototypes functioned, but functionality alone didn't validate the seven-tier concept. Zeta needed to verify that the system maintained performance across its entire configuration range. A design that worked perfectly in one setup but degraded in another hadn't achieved true modularity. It had simply created multiple separate configurations sharing common components. The barrel change testing proved particularly demanding. Quick change systems had to balance speed of operation with consistency of lockup. Make the attachment too loose, and accuracy suffered as barrel alignment shifted. Make it too tight, and field changes became impractical. The XCR's barrel locking mechanism employed a rotating collar that engaged multiple lugs simultaneously, distributing stress evenly while providing tool-free operation. Early prototypes showed promise, but achieving consistent return to zero across hundreds of change cycles required refinement of tolerances and surface treatments. Caliber conversion testing exposed different challenges. The 5.56 45mm NATO, 6.8mm Remington SPC, and 7.62 CAC 39mm Soviet cartridges generated different pressures and operated at different curves. The self-regulating gas system had to accommodate this variation automatically. Initial testing revealed that the gas system functioned well within each caliber, but required optimization at the boundaries. Configuration changes where ammunition pressures changed dramatically. Zita adjusted the gas piston's regulating mechanism, refining the spring rates and valve geometry until the system maintained consistent cycling across all supported calibers without manual intervention. The ambidextrous controls underwent evaluation for both mechanical reliability and operational intuitiveness. Left-handed users sometimes developed muscle memory for right-handed controls through years of adaptation. The XCR's equal access philosophy meant both sides had to function identically. Testing identified minor ergonomic differences in how controls felt depending on which hand operated them, leading to adjustments in lever geometry and throw distances. The goal wasn't simply making controls accessible from either side, it was ensuring that either side felt like the primary interface. Magazine compatibility testing verified feed reliability across different magazine manufacturers and generations. AR-15 magazines had evolved through decades of production, with variations in follower design, spring rates, and dimensional tolerances. The XCR's lower receiver geometry had to accommodate this variety without sacrificing consistency. Testing included both new magazines and deliberately worn examples, ensuring that the system functioned across the full spectrum of conditions users might encounter. The folding stock mechanism's testing focused on lock-up rigidity and durability through repeated fold cycles. A stock that folded easily but developed play over time would compromise long-term reliability. Zita subjected the mechanism to accelerated wear testing, verifying that the locking surfaces maintained engagement through thousands of fold and deploy cycles. The mechanism's simplicity proved advantageous. Fewer moving parts meant fewer potential failure points and easier maintenance. Environmental testing validated the entire system under temperature extremes, humidity variations, and contamination exposure. The self-regulating gas system had to maintain function in freezing conditions and desert heat. The barrel quick-change mechanism couldn't seize when contaminated with sand. The controls needed to operate with wet or gloved hands. Each test refined the design incrementally, moving the XCR from a functional prototype to a reliable system that delivered on its modularity promise across realistic operational conditions. The final curiosity, the seventh tier's complete integration with the preceding six, revealed itself not in specifications but in operational coherence. The rail interface system wasn't simply an accessory mounting solution, it represented the culmination of every prior engineering decision. Because the monolithic upper receiver centralized all structural loads, the rail could provide mounting surfaces that maintained their relationship to the bore axis regardless of configuration changes. Because the quick-change barrel system attached directly to that same upper receiver, barrel swaps didn't disrupt the rail's geometric relationship to the new barrel. Because the gas system self-regulated, accessories mounted to the rail experienced consistent impulses across different configurations. This integration solved a problem that had plagued modular designs: configuration-dependent zeroing. Many adaptable platforms required users to re-zero optical sights after reconfiguration, because structural flexing or changes in mechanical characteristics shifted the point of impact. The XCR's 7-tier cascade meant that an optical sight mounted to the rail maintained its zero when the user changed barrels, switched calibers, or modified the stock configuration. The mechanical consistency across configurations translated directly into operational consistency. Zita recognized that this 7th tier would determine whether the XCR succeeded as an engineering concept or remained merely an interesting technical exercise. Users could appreciate mechanical modularity in principle, but they evaluated hardware based on practical utility. If reconfiguring the system required re-establishing zeros for every mounted optic or accessory, the time saved by quick-change barrels disappeared into the time-lost re-zeroing equipment. The XCR's engineering had to deliver configuration freedom without operational disruption. The rail system's design reflected lessons from earlier mounting solutions. Picatinny rails had become standard by 2005, offering proven attachment interfaces and broad accessory compatibility. The XCR's rail implementation emphasized mounting surface stability. The rails were integral to the upper receiver rather than attached components, eliminating a potential source of movement or wear. This decision added manufacturing complexity, but removed a variable that could compromise the entire 7-tier system. What emerged was a mechanical philosophy, where every tier enabled and reinforced every other tier. The monolithic upper receiver provided the structural foundation that allowed the quick-change barrel. The barrel system's precision enabled meaningful caliber conversion. The caliber conversion flexibility required the self-regulating gas system. The gas system's automation enabled the ambidextrous controls to function consistently. The control's accessibility complemented the magazine compatibility. The magazine flexibility supported the folding stock's compact storage promise. The stock's simplicity preserved the rail system's mounting integrity, and the rail system's stability completed the loop, providing the operator interface that made every other tier's capability accessible and usable. The Robinson Armament XCR appeared in 2005 as a complete system, not as a platform awaiting future upgrades or modifications. Every mechanical element reflected intentional engineering decisions made in service of a unified modularity concept. The design didn't ask users to choose between adaptability and reliability, between configuration flexibility and operational consistency. It demonstrated that with sufficient engineering integration, those qualities could coexist in a single mechanical system. The XCR's legacy developed gradually. Initial market reception was cautious. Potential users appreciated the engineering sophistication but questioned whether the modularity justified the platform change from established equipment. Official organizations moved slowly toward adoption, conducting extended evaluations that tested the 7-tier concept against operational requirements. The civilian market showed interest sooner, particularly among users who valued configuration flexibility for training and collection purposes. What the XCR demonstrated extended beyond the device itself. It proved that modularity could be engineered as a core principle rather than implemented as an accessory feature. This philosophical approach influenced subsequent development across multiple manufacturers. The concept of hardware as adaptable systems rather than fixed objects gained credibility. Design teams began considering modularity earlier in development cycles, building flexibility into foundational architecture rather than adding it later through conversion kits or aftermarket modifications. The 7-tier cascade became a case study in systems engineering. Each tier had to succeed both independently and as part of the larger whole. The monolithic upper receiver had to provide structural strength while enabling other tiers' functionality. The gas system had to regulate automatically while accommodating the barrel system's quick-change nature. The controls had to serve ambidextrous operation while integrating with the magazine compatibility. This interdependence represented sophisticated engineering coordination, each mechanical element designed with awareness of how it connected to adjacent elements and to the system's overall operational logic. By demonstrating that true modularity was achievable without fundamental compromises, the XCR influenced market expectations. Users who had accepted that configuration changes required technician intervention or that caliber conversion meant accuracy degradation, now had evidence that engineering could solve those limitations. The system's existence raised questions about other platforms' design choices. Were certain limitations genuinely necessary, or were they artifacts of design philosophies that treated adaptability as optional? The XCR's manufacturing approach also offered lessons. Building a genuinely modular platform required tighter tolerances, more sophisticated machining, and more complex quality control than conventional hardware. The monolithic upper receiver demanded CNC precision across more surfaces. The barrel quick-change mechanism required consistent lockup that didn't degrade with wear. The self-regulating gas system needed components that maintained dimensional stability through thermal cycles and pressure variations. These manufacturing demands increased production costs, but delivered operational capabilities that couldn't be retrofitted onto simpler designs. Looking back from 2026, the Robinson Armament XCR occupies a particular position in engineering history. It wasn't the first modular design, nor was it the most widely adopted, but it represented a complete expression of modularity as an engineering philosophy. Every mechanical tier existed to support every other tier, creating a system where configuration changes happened fluidly, without sacrificing the reliability or consistency users expected from fixed platforms. The hardware demonstrated that adaptability didn't require operational compromise. It required integrated engineering that treated modularity as the foundation rather than the feature. The XCR's 7 tiers remain its defining characteristic. Not 7 separate features, but 7 interconnected layers of a single mechanical concept. That integration, more than any individual technical achievement, explains why the design continues to inform discussions about what modular engineering can accomplish when pursued as a coherent systems-level discipline rather than a collection of convertibility options. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.